Okay, our third session this morning, Arthur Larson. Arthur Larson started out in the U.S. Navy, 1959 to 1962. He was an electronics tech and also worked with some of the computers. As a matter of fact, the Navy was instrumental in the development of computers because they needed them before anyone else to figure out how to shoot large guns and make the shells land where they were supposed to. And then after that, he went to work for Spare Univac for 20 years, again in the computer business. And he ended up being a major engineer, instructor, and working quite a bit overseas. He retired in 1984. He'd been studying relativity for 20 years and decided to write a book about it. He had one paragraph to write on gravity in 1990. Well, that's now grown into a 400-page manuscript. So here's Arthur Larson.
Thank you. I'll trip over that yet. Well, thanks for having me. Before I get really started here, I really want to thank TeslaTech. There's not many venues where people with odd ideas can get it out to other people. And anybody that comes up with a new invention that may go against the status quo or a new idea, you will find that there are a lot of rocks in your path, not just from the military or the industrial complex. That's a term I'm sure you haven't heard since about 1965, but it shows you where I'm coming from. But you also have the government and science itself. Science is very, very touchy about what it knows and what other people know and how they let people know what they should believe. So if you come up with something different, they're probably the people that throw the rocks in the road even more than anybody else. So when you have a forum like this, like TeslaTech has been setting up for the last few years, it is probably one of the nicest things that could happen to those of us that are kind of like on the soft underbelly of science. And so I just want to say a nice hand to TeslaTech and the people here that make this possible. I should also like to make a comment about the other speakers and the potential for speakers that are sitting in this audience. We don't really get paid too much. In fact, as most people that have ideas that concentrate and spend years trying to develop something, probably never get paid a dime for it. This is usually a labor of love. They believe in what they do. They want to get it out to the people. They think it'll make a difference. And as a result, you'll see people who have been working in things for 20, 30 years and are still in their plug-in. So to those people that are still in that arena, you know, you may get bloodied, you get dirty, and a lot of times you'll bend. But never, never will we ever give up. What I've got for you here today, I hope you're all going to enjoy, because hopefully by the time this hour is finished, you're going to understand how gravity works and how it's made. Newton originally came up with his theory, or his law of gravity, but all it did was describe the behavior. It never said how it worked, how it was made, or why. And Newton was once asked, you know, how does your gravity work? And Newton said, I don't deal in conjecture. He didn't know and he wouldn't even guess. His original formula was the force of gravity equals mass 1 times mass 2 over the inverse square of the distance. The inverse square of the distance is very simple. What it means is, right now I weigh approximately 200 pounds. I won't admit anymore. And I am 4,000 miles from Earth's center. If we were to build a ladder 4,000 miles high, and I crawled up that ladder and weighed myself, we've doubled the distance. So the inverse would be 1/2, the square of 1/2 is 1/4. I would then weigh 50 pounds. In my new theory of gravity, my new hypothesis of gravity, I should say, I say the same thing, so we can eliminate this particular thing from contention, and we will just deal with the product of the masses. Einstein, Newton's gravity was an attractive gravity. There were lines of force, just like magnetic lines of force, that attracted two objects together. Einstein said there was no such thing as gravitational force like Newton said. He said it's curved space. A mass like the sun stresses the space around it. So according to Einstein, the Earth is not going around the sun. According to Einstein, Earth is following a path, a geodesic in space. And because that path is curved, it follows around the sun. But as far as the Earth is concerned, it's going in a straight line. It may be considered kind of funny that somebody will come up and say, we don't understand gravity, science doesn't understand gravity, because they don't. But we have to look at other things that science does not understand. Some really basic fundamental principles of matter. For example, charge. Anybody can tell you that a negative charge on something is in excess of electrons. Well, what they can't tell you is what is that charge on the actual electron? What actually is it? We've got some mathematical theories, but nobody really knows. Then we have gravity itself, which I'm telling you right now they don't know about, but you guys are all going to know about it pretty quick. Inertia is something else. Science thinks inertia is linked to gravity, but they don't know how, and they don't know why. And then we come to magnetism.
We've had a request from the production crew, if you can stand behind the podium, then they can see your dry erase and everything all at one time.
Oh, okay.
So if you're able to centralize yourself right here.
I was actually trying to get out of the light. You notice how I was getting over like this?
You're most gracious.
Yeah. That light is something else. Except for some of the laughter sometimes, you don't even know you got an audience. You just really got to peer against this thing. Right, so where was I? Okay. Magnetism. Now there's a perfect example. Here you got two simple magnets that any school kid can have. He can try to force them together and he can try to pull them apart. And there's actually a physical thing that is causing those like poles to repel each other and the unlike poles to attract. And if we put some iron shavings on a piece of paper and shake it and put the magnets on it, you can actually see these field lines, okay? But we don't know what the field lines really are. We don't know what the force is that causes magnetism to work as it does. And I think one of my favorite stories on that was a university professor was asked by his students, how does magnetism work? And the professor thought for a little bit and said, well, he said, I guess it works that way because God wants it to. So we are in the same situation with light. We know, for example, that if an electron jumps from one orbit to a lower energy orbit, it gives off a quantum, a photon of light. What we really don't know is how did that photon actually get made? Why is it emitted at the time the electron jumps? Why wasn't it emitted before? Hopefully we're going to find that out. Here today you're going to find out how gravity works, and we're going to change your whole universe. And I hope we have fun doing it. Oh yeah, when I say we change the whole universe, we're going to do that. Sorry. Oh, that's nice of you.
Oh, shucks,
Thank
Ma.
you. I can get over it further. The new theory, the new hypothesis of gravity is going to be force of gravity equals 2 times mass 1 times mass 2 over the inverse square of the distance, which we are going to forget. This modification by a factor of 2 is going to have severe implications for just about everything that we do in space. The second prediction I'm going to make is that the gravitational constant, G, must be 2 times what it is today. Sorry, these things aren't quite. See if I can find the arrow when it comes out better. Oh, that should work. So we're going to double G. Now, normally, and if there's any physicists in the crowd, I think there are a couple, they immediately would rather jump down my throat and say, why isn't G up here like it should be? That's because G didn't come into the equation until 150 years after Newton came up with his law. We are dealing strictly with fundamentals, so we are going to stay right there. Now, if you take this equation of Newton's and you say that the force, we'll call it the 1, would, if we have a mass of 1 and a mass of 1, for the two masses, 1 times 1 equals 1. According to Newton, it doesn't make any difference which one you double. If we double mass 1, we would have 2 times 1, we get a force of 2. If we double mass 2, we will get 1 times 2, and again we'll get a force of 2. According to Newton, 2 equals 2. Force of 2 equals a force of 2. There's no difference. But we can prove that's wrong right now. Newton cannot handle certain things. For example, if we have a satellite circling the Earth, the satellite's in a certain orbit. We don't care really how high it is or what speed it's going. All we care is it's in an orbit. Now, let's call the satellite, say M1, and we'll call the Earth M2. All right? So let's assume that we just take the satellite and we double its mass. What happens to its orbit? Does its orbit change? Well, the easy answer is, geez, I don't really know. How can we double the mass of the satellite? Well, every time we send the space shuttle up and it docks, haven't we really impacted the mass of that satellite as a unit? This space shuttle is now part of the ISS. What happens to the orbit and speed? Absolutely zilch. It stays the same. According to Newton, if you had the satellite circling the Earth, then there's the satellite and there's the Earth. According to Newton, we got a rubber band between the Earth and the satellite, and if we double the satellite, we double the rubber band. But nothing happens. All right, let's just leave that there for a second. Now let's go down to the Earth, and let's assume that we leave the satellite as it is and we double the mass of the Earth, either by doubling its density or doubling its radius with an extra Earth worth of mass in it, however we want to do that. What now happens to the orbit of the satellite? The satellite must come in and go faster around the Earth. And we see that when meteorites come around, when asteroids come around, etc., and low orbit satellites. So Newton again said, here's our rubber band, and if we increase the size of the Earth, doubled it, we should again get this double rubber band. In other words, Newton is saying that it doesn't make any difference which one of these we double, we should have got the same thing out. And we don't. We get 2 forces out. We get 2 orbits. One when we double the Earth and one when we double the satellite. So that proves then that between any 2 bodies, there's actually 2 forces. And this is the key behind my new hypothesis of gravity. So let's find out how gravity really works. You all know how skateboards work. If you don't, I'm sure your kids will show you. But here we got a skateboard, got wheels, and here we got 2 people. I'll draw stick figures, and there's the nose pointing that way. Looks like Bob Hope. Another one pointing this way. And each one of these people has a fire hose, a high pressure fire hose, and it is shooting out. So we'll just say the water goes out, and we'll call this guy A and this guy B. Now, right now with both of them shooting water out with equal force, nothing happens. The skateboard will remain still. What happens then if we take A and we eliminate his water? He shuts his water off. The skateboard is going to go in this direction. Why? Because this guy still has water going out there and he's still got the recoil. All right? The fun begins when we have another skateboard. We have a second skateboard, again with a guy shooting water out in that direction, another guy in this direction shooting water out. This guy is still shooting now, okay? And we'll call this guy A prime and this guy B prime. Right now at the moment, A and A prime are shooting water at each other, and if the water from each one of them hits the other guy, it's going to shut off his water hose. And probably knock the guy down, but we don't care. But he's going to shut off the water hose, and these 2 skateboards, this one will now move in that direction. These 2 skateboards will now move together because of the recoils from within the water. and this is a self-movement. So gravity is not an attractive force, it is not a curvature of space, it is a self-movement. In other words, the atoms move themselves. The force to move the atom comes from within the atom. There is no outside force. If we call the skateboard and the people the atoms, and we call the water gravitons, and we call the recoils graviton recoils, congratulations, you've now just discovered how gravity works. As you sit here listening to me, the old way of looking at gravity was that Earth attracted you with a rubber band, and vice versa. The new way of looking at it is the gravitons from the Earth are being emitted to the atoms in your body. And if we were to draw this, as I should have done right off the bat, as you can see, I'm old school. I don't use PowerPoint very much. Fact is, I've never tried it. So if we have the Earth here and we have your atoms there, what's actually happening is gravitons from the Earth are hitting the basic sides of your atoms on the bottom side, and they are blocking graviton emission from that time. And gravitons being emitted from an atom, we're talking millions per second. So that means that the gravitons that are still being emitted to the top side thank you. So the gravitons that are still being emitted from the top side have their recoils, and their recoils are unbalanced. And as a result, these atoms try to move toward the Earth, and that we measure as weight. And I actually should give you that. What we have then is, forget it, there's an atom, and I'm talking about a hydrogen proton because that has one nucleus, one particle in the nucleus, and it has one electron, and we'll forget about the electrons for the moment. So that nucleus is giving off millions of gravitons. Each graviton gives a recoil. Now, do we know about these recoils? Yes, we do. They're called the Mossberg effect. The Mossbauer effect, if you emit a proton, or a photon, sorry, from a crystal, you give a recoil to the crystal. Nobody really knows why. Why should we emit a photon and then wind up getting a kick? Well, that is called the Mossbauer effect. We find that this is the same thing happening on the atomic level. Gravitons are being emitted. Every graviton has a recoil. So those little arrows that you see right there, those are the recoils. The little dots are the gravitons. So if you have an atom up in free space, and it's not being affected by any other fields, there's nothing there, that atom will be perfectly at rest because all the recoils are balanced out.
Oh, you got one.
I got one. I got a red one too if they want red. So what we have here then is two atoms. They're giving off gravitons. But you see right here, a graviton has come from this atom and it's hit this atom right there. And I show a little starburst. What it's done there is the graviton, when it originally left this atom, was at zero speed relative to the atom. By the time it reached the end of its atomic field, this graviton is going at a minimum light speed. When this graviton then hits this other atom at light speed, its energy must now be absorbed in the nucleus of that atom. And when its energy is being absorbed, the gravitons that should have been emitted from this area can't be emitted, so the ones that are coming up at this area are unbalanced. So this atom moves in this direction. Same thing happens here, vice versa. This atom moves in this direction, and it's a self-movement of atoms. If we go into Newton's 3 laws of motion, you will find out that every law that he has of the 3 uses an outside force to either change the uniform translation of a particle or a body, or to accelerate a body to give us inertia. And we find out that in gravity, all the forces are internal to the atom, based upon graviton interchange. All the graviton interchange does between two particles is sets up the condition to make the unbalanced gravitons. So it sets up the condition. Then, as I said, as you people sit here then and listen to what I'm having to say, gravitons from the Earth are hitting your atoms basically on the bottom side. Sure, you're getting some from the air, from the building, from the top, but compared to the Earth, it's minuscule. So your atoms then are trying to move themselves down, and that is what we call weight. The thing to remember with this should set off a few bells. If your gravitons can force you down right now with a force of whatever, 100 pounds, 150, 200, 250, 300, I think we got at least one 300-pound guy up here. I wouldn't run and get in an argument with him. And if they can force you down, why can't they force you up? Just as easy. And all we have to do is figure out how can we mimic this action down here. If we could mimic this action up here and get the unbalanced gravitons going off the bottom, this atom would take off in that direction, and so would you. Einstein made a comment, and we showed it at the very beginning, that for any new idea you must have free invention of the human mind. I've only done one thing different from what everybody knows, and I have said that when you have a graviton impact, you get the unbalanced gravitons, and their recoils are the motive agent. Okay, this is my original logo. Isn't low-tech wonderful? High-tech, everything's perfect right there. Low-tech, you got to work it out. So for the creation of a theory, the mere collection of recorded phenomena never suffices. There must be always added a free interpretation of the human mind that attacks the root of the matter. In case there are any people in the audience that don't believe in gravitons, we have a book here by Stephen Hawking, A Brief History of Time. And you've probably all seen Stephen at some time on TV. He's got MS, he's very crippled up, and he talks to a voice synthesizer. He is probably today's foremost, most intelligent, and well, perhaps the best theoretical physicist on the globe today. And here's what he had to say about gravitons. In the quantum mechanical way of looking at the gravitational field, the force between two matter particles is pictured as being carried by a particle of spin 2 called the graviton. This has no mass of its own, so these are massless particles. So the force that it carries is long range. The gravitational force between the sun and the earth is ascribed to the exchange of gravitons between the particles that make up these two bodies. And here's the key. Although the exchange particles are virtual, they certainly do produce a measurable effect. They make the earth orbit the sun. It's all here, and this thing is, you can get it in any bookstore. So it shows that even somebody like Stephen Hawking is basically saying it's not curved space. But just like Newton, who didn't know how or why his gravity worked and said, I don't deal in conjecture, Dr. Hawkins is in the same situation where he says, yes, it's due to exchange of gravitons, but why, he doesn't know. This is what we're finding out. Okay, slide 2, yeah, we got that, all right. And by the way, the reason we have this week crawl is because, just show that, one of that first slide showing the atom with all the gravitons. Anyone will do. Yeah, that'll be fine. The reason we have graviton recoil is quite simple. Even though gravitons have no mass, they are mass free. what happens is they have to be at 0 speed relative to the nucleus when they first are emitted. By the time they reach the atomic limits of the atomic field of that particular atom, they have to go at least light speed. Later on you'll find out where I'll show you that gravitons travel faster than light. But at the moment, they go at least light speed by the time they hit the end of the atomic field. The distance they travel is 10 to the negative 8 centimeters, and they do that distance in 10 to the negative 21st seconds. So that's 10 with 21 zeros. This tremendous acceleration of the graviton through that atomic field, even though it has no mass, is what gives that recoil. It gives that kick. And because of this, we're going to be able to do many, many things. The beautiful thing about this theory of gravity, and I shouldn't call it theory, it's hypothesis. A hypothesis is something that hasn't been proven yet. And this has not been proven. We have an experiment to do it, and I'm going to go into that, but it's still not proven. So it remains a hypothesis, and this is why they call it theory of relativity, the theory of relativity, because it's considered to be proven. Scientists love to use buzzwords in opposite ways that the layperson uses. So when you say theory to a layperson, well, that's just a theory. It hasn't been proven yet. No, that's a hypothesis. The theory has been proven. The science says that every hypothesis, in order to be taken seriously, must give quantitative predictions that can be experimentally tested. Now, by quantitative predictions, what we're saying is these predictions must be measurable. You must be able to make your predictions, measure them, and then you must be able to test them. So what I said on the whiteboard before, that G must double and Newton's law must be modified by a factor of 2. We're going to show that these two predictions, they are quantitative, they can be measured, and we have the experiment to prove it. The beautiful thing about this form of gravity is we don't need attractive force, we don't need lines, gravitational lines, we don't need stress space or curved space, we don't need velocities through space being limited by our speed relative to the Earth through space. Okay? We don't need distances changing as we go through space, actual distances shortening up. There are many, many things we don't need. We don't need slow time, variable distance. We don't need massy light. We don't need strings or loops or brains. And we don't need multi-dimensions or any other such what I call insults to nature. Everything we're going to do, we're going to use, gravitons are going to act in the same way in every case. We're just going to utilize their actions differently. Now, slide 15. Back in 1798, Henry Cavendish made an experiment to determine the gravitational constant. And what he did is what we see on the board. He took 2-inch lead balls, 2 inches in diameter. There's another one over there got scraped off. And he put them on a torsion wire, a hanger. And this torsion wire was 39 inches long, 2.4 grains per foot. And I was jumped on one day by a physicist who says, how come you're using grains per foot? You could be using something else. And I said, because that's the way I showed it in the book. And that's the way, and I don't know the conversion. So that's the way he did it, that's the way it is. And then he had a pulley here with a rope attached to it. And then he had 8-inch lead balls. And on one of these smaller lead balls in the corner, he had a little marker, and then he had a scale marked on the apparatus. And what he did, he measured how this ball was attracted here and this ball was attracted there, and it made a torsion, twist to the wire. This is why it's called torsion balance. And then he took the pulley and rope and he moved this ball over here and this ball over here, because now it should be attracted, using Newton's terminology, it should be attracted to the other ball. All right? And that was to check himself, see if he got the same deviation each time from the set point. I myself built an apparatus like this in my home. We had a large building, a large room which we added to our home, and I covered everything up. I put everything in a Faraday cage, and I would sit there and I'd watch, just not with these big weights yet, but just with the small weights on a torsion wire, and I had a laser light bouncing off a mirror, and that thing would go about 8 foot from side to side from the center point, and it would never stop moving. I had a video camcorder which would set up for interviews that intervals that I could sit and watch this thing, and I'd just be all day, all night, all week, next week, and you just couldn't make it quit. And one night I had a physicist come over, and he stayed overnight. Next morning we're sitting there watching it through binoculars, through the glass doors, and we saw the light go from the center point, we'll say it was right here, we saw it go up about 8 feet. It came back just as fast as everything, nothing's different, and it was, you know, getting ready to come over here. But when it got to here, and thank God he was watching it, when it got to here, all of a sudden it stopped, and it went that way again. And this guy just about fell off his chair. He says, "My God, you found anti-gravity." Well, the only thing we could come up with was that there are anomalous gravitational pulses coming from the Earth. And when this thing had moved back and forth and sent the light beam out and come back, we must have gotten one of those pulses. And that's the only thing he could come out. So we come to the conclusion that for a layperson to do this experiment, and even though it's very, very simple, it's quite hard to do. It needs to be done underneath a mine someplace with the resources of a university or of a government. I learned by the years that I had this thing set up, and you can ask my wife, that it was set up for a couple of years. Okay, I learned that I myself could not get the fine control that I needed, because if the wind blew and the trees moved, if my wife walked between the living room and the kitchen, if a car drove up, I could see all that. And it really screwed up the measurements. So, the reason I say, by the way, that Cavendish must be doubled is because these large balls on the rope and pulley, any gravitational movement that would have been induced in them by the small balls would have been overridden by the friction of the rope and pulley. And if you understand how small gravity actually is, if you had two locomotives and you hung them up by a chain, and those two locomotives were pretty close to each other, the amount of attraction between those two locomotives would be about the weight of a penny. So you can see what you're talking about when you're trying to see something this small. I once sent this thing to a NASA scientist, and I told him that G would have to double. And I told him why. Forget about why I told him why. He didn't even look at it. He come back to me and says, "You know, if you are right and G has to double, then the stars are going to have to change their courses. Little birdies are going to fall out of their nest." And that was from a physicist. I couldn't believe it. This guy really was a physicist. Where the hell did he get his degree from? If we find out that the gravitational constant is double, all it means it's going to tell us is that the force that we thought was there originally is now doubled. But it hasn't changed anything, because whatever it was before, it was now. You haven't changed the force. You just merely measured it more accurately. Okay, now we're going to go into the experiment, and I'm going to try to show you on the whiteboard how this works. And I hope everybody can see this okay. Remember what Newton's law said? Force equals mass 1 times mass 2. So what we're going to do is we're going to draw a circle here with a 1 in it. That's going to be 1 mass, and that's going to represent 2 masses on a swinging torsion wire. And then we're going to draw another one here. That's also going to be 1 mass and represent another hanger on a torsion wire. And according to Newton's law, 1 times 1, you get a force of 1. All right, very simply then, let's take mass 2 and we'll double it. Must be some grease on this board. Anyway, and we'll leave the other one here at mass 1. And now we're going to get 2 times 1, we're going to force of 2. Now if we do the same thing and we double this one, leave this one at 2, now we're going to get 2 times 2 and we're going to get a 4. That's the way Newton's law, what it's going to give you. But now we're going to see something different. It's coming on the screen shortly. We do have it. I think you've got it there, Sonny, don't you? It's in the paper. Can you put that on? The first one? The one you got on top right there?
This one?
Yeah. You're trying to say my drawing isn't very good?
Use a different marker, please.
So here we have it. We have two masses, one each. We get a force of 1. We double this one. This times this because it's a force of 2. And we double this one, double that one, and we get a force of 4. Disregard this barrier here for the moment. That's what Newton's law would give us. Now we're going to see how, if this is because of graviton interchange, we're going to see how it'll work our way. And I'm going to put this on the board and then we'll put it back on the screen. The reason I'm going to put it on the board first because I want to develop it. And I don't want you seeing everything and then wondering what's going on.
I can't see your marker.
That doggone thing. Let's try a different one. Try that? No good?
Try black.
Well, I've been working on black. Let's try it again. There we go. Okay. Thank you. We'll put it on the screen shortly, but I want to develop this. Let's start out with our reference spheres again, each with a mass of 1, with a force of 1. But what we're going to do a little different here, up here we're going to draw another little circle. And this circle is one atom, and it represents all the atoms in this sphere. We'll draw another little circle up here, and this represents one atom of all the atoms in this sphere. Then we're going to draw a little arrow. And that arrow is going to be the gravitons hitting this sphere coming from this one. And this arrow is going to represent the gravitons coming from this one for each atom. Next thing we're going to do is we're going to draw down our original conditions. We'll bring this one down as mass 1, but on this one, we're going to double the mass. So what have we done? We now have 2 atoms here, and each atom still gets the number of gravitons, same number of gravitons, and so we have 2 atoms, each with 1 graviton apiece on this side. So this mass sees a self-movement of 2 times. All right, over here, we left this the same. But we've doubled this one, so we're getting twice as many gravitons from this mass, so we wind up with 2 arrows on this single atom. And again, we get 2 times the self-movement. We add these together, okay, and we wound up with 4. We'll do one last one. Again, we'll bring down our conditions. I'll draw the 2 atoms over here. 1 arrow apiece. Over here I'll draw the 1 atom with 2 arrows. And now we'll bring this one back down. We'll leave it at size of 2, and now we will make this one a 2. If we make this one twice the size, we must double the number of atoms. Each one still receives 2 gravitons from there, and so now we are 2 times again from what we were here, but from what we were here, we're 4 times, because we not only have twice as many atoms, but we have twice as many gravitons. So we actually wind up, for the total of this one, 4 times. Then we come over here, because we have doubled this one, we now wind up with 2 gravitons each one. So this one doubles again from what it was here, but from what it is up here, it's 4 times. So we wind up with 8. So in this new gravity, instead of having 1, 2, 4, we have 1, 4, 8. We have doubled Newton's law. And so that is now properly F equals 2 times mass 1, mass 2. If we were to take a barrier and we put that barrier right down in front of these atoms, or these masses, so these cannot move, then we're going to get 1, 2, 4. In other words, if these masses cannot move, we will get Newton's law if we try this experiment and we double the masses. And then you got that second one on there?
Yes.
There you go. So what I've drawn there, we now have on the screen. And we see we get 1, 4, 8. And we see why. Because the atoms and gravitons all combine to double what we see. This then is the experiment which Cavendish, we use a modified Cavendish experiment. Instead of having just one swinging set of balls, we need 2 swinging set of balls. And if you don't think that isn't hard to do, you've never tried the experiment. It is bloody hard to do. So, doing this experiment though, if we wind up with Newton's law each time we double the sphere, and Newton's would be 1 times 1 equals 1, 2 times 1 equals 2, 2 times 2 equals 4. So if we wind up with Newton's law, that proves my theory completely wrong, my hypothesis is wrong. However, if we get what I say we get 1, 4, and 8, and on down the line, that will then conclusively prove the predictions and thereby the hypothesis. If that is true, not only does Newton's law need to be modified, which it can be done very easily, but Einstein's curved space gravity is now wrong. I submitted this abstract to SDIF-04, and they accepted it and everything. And just before they finished the acceptance procedures, all of a sudden I get a letter saying that my paper would be withdrawn. I would not be allowed to speak. When I called them up and asked them why, they said, because your theory does not reduce down the general relativity. Well, I'm not somebody to say yes sir and kiss somebody's behind because he happens to be relativity. This new theory, if it destroys Einstein's gravity, so be it. But you see, science has got too much invested in it. They don't want to hear something like this. Einstein himself said that I could be proven right 1,000 times. It will only take one experiment to prove me wrong. If this one is successful, that's the experiment. Okay, now we'll go on to the inertia. Okay, we'll leave that one for a second. Now we're going to see how inertia works. And right now, I got another slide that will explain it a little bit better, but I want to show this one. This again is the proton, hydrogen proton, and these are the frequencies of the gravitons, and I showed them in a waveform because I wanted to show that if you accelerate this atom with an outside force, that you're going to pile up the waveforms, you're going to pile up the gravitons, and when you pile up the waveforms, you're also going to pile up the graviton recoils. Leave the papers down for a second. So what we're going to have here then, the same atom, you accelerate it, and all these little dots, this thing got an on-off, shit, there we go. All these little dots are the gravitons, and what happens is the gravitons pile up, and as they pile up, it's like an FM wave. If you have an FM transmitter, what they do is they take the carrier, and if they want the low side of the sine wave, the audio wave, they stretch the carrier out. If they want the high side, they bring it in compression. All right? So what we have here then is we have the gravitons being compressed into a packet, and that packet has a lower frequency envelope. Gravitons have to be the highest possible frequency and the lowest possible energy. So that means that the size of a graviton, here we go, the size of a graviton has got to be about the Planck length, which is 10 to the negative 33rd centimeters. That's the smallest possible thing in the universe, according to science. And if it is, then that's the size of a graviton. The energy within a graviton, again, has to be the smallest possible energy. And that also was done by Planck. Planck's energy limit, I guess you'd call it. So we see then that if gravitons are very, very high frequency, we can't see them. We can sense them, because that's what keeps us from falling over, keeps us down. It is possible, and I'm theorizing this, that if you take an electron, and anything, by the way, that has mass is giving off gravitons. So that means an electron's giving off gravitons too. And when you take an atom, put heat to it, and the electron jumps, this is what happens. The electron actually compresses the gravitons. That compression then, the recoils are piled up, and that resists the motion of the atom. That is inertia. Now, take off those two yellow pieces. And this is interesting. If this low frequency envelope is high frequency enough, in other words, if the atom or the electron jumps fast enough and keeps going faster and faster, it's going to pile up more and more gravitons. It's going to give us more and more resistance to the acceleration. And eventually, that little thing right there is going to become a photon of light. And when it hits the correct frequency, we're actually going to see it with our eyes as light. So, if you have a rock and you try to throw that rock, you feel a resistance to your throw. That's inertia. You're piling up its gravitons, and light is made exactly the same way. There's no difference. But light is made by a much higher rate of acceleration. So, throwing a rock or making light, no difference. Gravitons, how they work, what they're doing the same thing in all cases. We're just utilizing a different way. We now get into, if this is light, why is a black hole black? You think, well, that's kind of a stupid question, because it doesn't emit any light. Now, that's a no-brainer, isn't it? But stop and think. When you get outside matter, from crashing into a black hole, before it gets to the singularity, this matter is undergoing tremendous torsional, compression, gravitational influences, and it's giving off light until finally it gets below the event horizon. At the event horizon, the number of gravitons is so great, and these gravitons are going through these photons of light and dragging them down or breaking them apart, whatever you want. Below the event horizon, then, we cannot see light because photons cannot escape. So, right at the black hole itself, the gravitation intensity is so great, and I'm talking billions and billions and billions and billions, times what we see here on Earth, is that any photon that is going to be emitted by an atom or an electron being accelerated is immediately going to be flooded with gravitons that are just going to whop that sucker right down. And its energy put back into the black hole. All right, now this gives us another item. There were two things that Einstein used to prove his theory. One was that we would take a beam of light and it passes close to the sun. That beam of light would be bent. And this was verified in 1919 by Arthur Eddington. So if we have, say, the sun sitting here, and we have a beam of light coming here, according to Einstein, what should have happened then, this beam of light should be bent. So originally, if we had a star sitting here, because of the bending of light, we would see the star over here. So what they did, they went out during a solar eclipse of the sun rather, same thing, and they took photographs of the star sky before the eclipse, and then they took photographs right when they were in the middle of the eclipse, and they looked at the stars, and sure enough, they found this apparent bending. And so one of Einstein's predictions, by the way, Newton also made the same prediction in his Principia Mathematica, but Einstein made a better one. So this was touted then to uphold Einstein's theory. So let's look a little bit differently. Let's assume, again, you've got the sun, and you've got gravitons from the sun. Well, let's just show them going straight up. And they're going at least at light speed, which is small letter c. and you got a light photon coming down through here. When this light photon is hit by this graviton, don't forget the light is going that direction at the speed of light. This photon is going at this direction at the speed of light, if not faster. So we have an effective intersection at a 45-degree angle. And what happens then is this graviton must propagate through this photon until it hits the other side, in which case it takes off again. Now, if you don't believe that light can slow down and take off, look at light through water. It travels at a different speed through water. That's why we get the refraction effect. But when light leaves the water, it speeds right back up to light speed again. Same with the gravitons. The graviton comes through, and if you have enough gravitons coming up from the sun and going through this effectively at this angle, that you are going to wind up causing this photon to divert. And what we've done, we've effectively bent the beam of light. So we can explain the bending of light by the graviton theory. The second thing that proved Einstein's relativity was the precession of Mercury's orbit. Mercury is on an elliptical orbit. It goes way out here, and then it comes in near the sun, and then goes way back out again. And what happens at the perihelion point, which is the nearest point from Mercury's orbit to the sun, every century there's something like 560 degrees of advance. Well, when we figured out, I think it was 1845, just before Neptune was discovered, they figured out how much of this advance was due to the planets. Jupiter was, of course, the biggest one. And they figured out that there would be 43 seconds of arc per century that was left unaccounted for. When Einstein's relativity came out, he said, right, this relativity, and he had the calculations to prove it, will explain this 43 seconds of arc. And so this was the second proof. But let's see what's actually happening. If you have Mercury coming by and it's coming past the sun very fast, when it's way out here in its orbit, basically the photons, the gravitons from the sun are hitting it at a certain angle. Way out there, it's almost at a 90-degree angle. But as Mercury comes faster and faster, these gravitons now are effectively hitting Mercury more at a slant. And what happens if you have an atom and you are being hit by gravitons, you set up a vortex, unbalanced gravitons give a recoil and tends to speed you up, plus you're eliminating gravitons you're eliminating gravitons from here, so you're lessening its inertia. So what you're doing then is the gravitons from the sun hitting Mercury at more of a head-on direction are eliminating inertia in this direction, and they're adding force in this direction, and so Mercury speeds up. Are we getting there?
Yeah, Art, I want to ask you a quick question.
Sure.
About how much longer do you think you have? Normally, this is about the time we break for lunch, but I'm really into this. How about you guys? You know, the only reason is, we're going to crowd our lunch. We want to just ask everybody's, well, how long?
How long have I been on?
Oh,
Half hour?
About an hour and 10 minutes.
Have I been on that long? Sorry, guys.
Or 12 minutes, actually.
Passes fast when you're having fun.
No. This train of thought you're going on, this path. How long will it take you to finish this?
Not too long if I cut it short. I got one more thing. We haven't destroyed the universe yet. We got more than one thing.
10
I
or
guess.
15 minutes?
Yeah, at the most.
10 or 15 minutes, okay, everybody? All right. I noticed there's a little bit of wash over here on the screen. If I pull this way, that way that little bit of projector shine, hopefully that'll make it visible, a little easier for you guys to read.
I keep trying to work my way over to this section of the fence. Oh. All right. We'll skip the laser experiment, although that was kind of fun. I'll just mention it. But what I want to show then is maybe we will. We'll see what time we get. How do we look at the universe? If you look at before 1913, we thought that the Milky Way was the entire universe. We didn't know any better. But there were little fuzzy areas called Messner objects, And we thought these were nebula within the Milky Way, and this was all there was. In fact, as Einstein once told a friend of his, that the universe is only 100 million light years across, and that was it. All right? What happened then is if we had, a fellow by the name of Slipher in 1913 had a 6-inch telescope, and he looked at these objects and he found out they were actually galaxies. And this is the first time we figured that there was stuff outside our galaxy. It's only 1928, it's less than 100 years ago. I mean, we are really in our infancy as far as astronomy, cosmology, and so forth, and the understanding of our universe. So, he looked at 15 different galaxies, and of the 15 he looked at, about 11 or 12 showed a redshift. They were going away. Now, why did redshift get put into recession? Why does redshift imply recession? That's because if you take a photon of light and it's traveling through space, according to science, this photon of light does not lose any energy. And it actually sounds pretty good because we can look out 13, 14, 15 billion years and we can see little stars, and that photon we are seeing has traveled for 15 billion years, and it's still a photon. So, science says then that these light photons do not lose energy over distance. So therefore, why do we get a redshift? Well, if you're standing at a train station and the train comes toward you and it whistles, it goes, whoo, okay? And then when it goes away, it goes, whoo, all right? In other words, it increases the frequency coming toward you and goes lower frequency going away. That lower frequency is the same thing as redshift, as far as light's concerned. It's called the Doppler effect. All right. Science also tells us that in every cubic meter, there is from 1 to 10 atoms in space. So space is not empty. Space is a medium, but it's very rarefied. So what happens, if you take Hubble, let's continue on. Hubble then, in 1928, took the Mount Wilson 100-inch reflector, and he looked up and he said, my God, he said, as I go further and further out into space, I get more and more and more redshift, and it came out to be 10 miles per second per 1 million light years. Doesn't sound like much, but if you're talking a couple billion years, you're talking an awful lot of these square or cubic meters. And if you're talking, say, like 1 million light years, you're talking like 12 to the 21st number of cubic meters that are all in this pathway. So if you got 12 to the umpty billion of these things, a photon of light, as it goes through these things on the way to us over 1 million light years, is now and then going to hit a few of these fields. And when we have an atomic field, atom here, and here you have a photon of light coming through, it must propagate. If it hits the nucleus, its energy will be put into the nucleus and it will disappear from the universe as far as it's concerned. But if it passes through, when it gets on the other side, again, it travels at light speed, all right? But it's lost a little bit of energy. And when you lose a little bit of energy, that equates to lower frequency, more redshift, lower energy, okay, and lower frequency. So, because science said that light does not lose energy over space, then the redshift that Hubble saw had to be due to recession. What if this little assumption that light does not lose energy is wrong? And therefore we look at this and we say, well, if light has to propagate through some of those atomic fields over 1 million, each average, an average number per 1 million light years, then this propagation is going to result in redshift. If this is true, if redshift is really because of distance, not because of recession, or it could be recession, but not as much. If it's basically due to distance, before when we looked at it, you're flashing red light saying, I got to get out of here, okay. Before when you look, I'm a quick learner. Before.
Redshift?
Yeah, we're talking about redshift. Boy, you know, senior moment, okay. You got me off my side. my track of light, or my track of thought. Somebody said, what happens if we turn time around? Instead of these things going away from us at these great big red-shifted speeds, let's turn time around. And he found out that, you know, about 15 billion years ago, everything in the universe that we see was in this one little atom. And I mean one little atom. Some people say it's big as a grapefruit. Some people see like the size of a pea. Others say it is one atom. And therefore, for us to see an expanding universe, then this atom must have exploded. Or, as scientists like to say, it inflated. They don't like the idea of explosion. So it inflated. And this is what we see in the expanding universe today. And it's all based on this little assumption that light does not lose energy over distance. But yet we see that space with 1 to 10 atoms per cubic meter is actually a medium. It's very rarefied, but it's still a medium. And if light travels through space long enough, it's going to go through that medium and it is going to get redshifted. If it gets redshifted, then we don't have an expanding universe. There never was a Big Bang. We are in a flat universe. And there may be areas in the universe where areas are contracting, where areas are expanding, all due to gravitational influences, okay? But basically, we live in a flat, non-expanding universe. And one of these days, people are going to wake up to that fact that this is what's happening. This is what's causing redshift. We cannot any longer afford to forget about our fundamentals. And this is what's happening in science today. They build these houses of cards on their assumptions, and they forget what the fundamentals were, and they forget to go back to them and say, now, are these fundamentals right? All right. We are running short. I guess we've got to get out of here. So I was going to do a laser experiment. We'll just talk about it just for a second. Well, yeah. All right. Right. Now let's see. Let's just take this off of here.
It's heavy.
That's right. Oops, I need some. Yeah. Need a couple thingies out of here. Need that. How's this for a honker of a laser, huh? Don't want to get that in anybody's eyes. And you see the socks coming out of here, you know I'm from Minnesota. Now let's set this up here. Probably aim it over that way. Yeah. Make sure we're aiming the right section.
Yeah.
You can plug that in, please.
You want me to?
Yep. We on? Oh, there we are.
You know that was a brand new screen before you burned a hole in it.
I'll try not to burn it up. Can we dim the lights?
Dim lights.
Okay. Can you all see what's on that screen? We got somebody's body in the way there. Okay. What you see there, you see a light pulse in the middle, and then you see coming out on both sides, light, dark, light, dark, light, dark. Now, if you can't see it, feel free to come up and take a look. Because what we have here is we have interference patterns through a single slit. If you ask any scientist, and I'm sure there's a couple here listening to this, that this cannot be. You cannot get interference through a single slit.
right
There,
now. One
there we are,
step.
right there.
Okay, cam 4,
All right,
back one more step.
if you look,
Back up right in that corner right there.
oh, okay. If you look at any book on science, any history, any chemistry book, any book on physics, Brian Greene, The Elegant Universe, does a good treatment of this. And they talk about the two-slit experiment because they say you got to put a light through two slits and then they will interfere, and that proves that light is a waveform instead of a particle. Well, we know light is a particle, but we can still get the wave, the interference, and we can do this with a single slit, which all the books say you cannot do. And I have books here, and I have articles printed out. Anybody wants to see it, anybody, including Stephen Hawking, says that this is impossible. You cannot get interference through a single slit. And here we have it. I have two razor blades. And the fact is, if I wanted to show a little bit further, I could take one razor blade away, and we will see a half circular pattern with interference. So, if you read books, there's always somebody in the crowd. Now, it's hard to see because the laser is that bright, but if you look in the upper left-hand corner, if somebody down here wants to take a look at it and verify it, you can see the circular pattern, the interference patterns.
Kind of like the half moon.
Yeah, half moon, but it's light, dark, light, dark. You can actually see it. And this is only using one razor blade, so I'm not even using a single slit. And this was done to prove that light was a wave, and it was also done to prove quantum weirdness. When they put a single electron through a slit, what you're supposed to just see is a bright spot, or a bell curve. And then if you open up the second slit without putting the electron through that slit, all of a sudden you get the interference pattern, and this is supposed to be proof of quantum weirdness. Well, we're showing here that just through that original slit, they would have had the interference pattern. So it was just something quick I wanted to show you, because you wonder sometimes when people don't believe everything that scientists tells them or tell them. It's because so many of our scientists never go to fundamentals. So that was just a quick and dirty. I'm sorry I couldn't. I had a whole bunch of stuff, other stuff, but when I originally came here, I only thought I had an hour, so I'd leave some stuff at home. But maybe we'll hit that again at a separate date. Thank you all very much.
Ladies and gentlemen,
Sure.
I would love to get to it.
Okay.
Hold on just a second.
We'll go ahead and start the lunch about, after lunch, about 10, we'll make it about 10 or 15 minutes.